Testing, can you hear me? Testing again. Can you hear me? I have the chat on, but I won't be reading it live. Okay, this stream is public now, so I am a little sick today. That's why I didn't stream for like a week. Also, my voice is kind of weird right now. I had to adjust my mic, so I would sound a bit weird right now. Sorry. Anyways, last stream. Wait. Also, I put this tag on the top because feel like some people are viewing me as an educator. I'm more like a learner. Anyways, so last stream we were talking about the processor, and the processor has 5 stages. The instruction fetch stage, the operand fetch stage, the execute stage, the memory stage, and the register stage. Now, the thing is, in order to save time, uh, hold on, I should do it over here. I'll try to explain it. You have the instruction fetch stage, then operand fetch, then execute, then memory, and then register. Now, like let's say the first instruction 1 is being executed. Instruction 2 and 3 will are the next instructions to be executed. So we start with instruction 1. It's in the instruction fetch stage. But then in the next clock cycle, it will move on to the operand fetch stage. But instead of waiting for the instruction to complete before starting instruction 2, they would like start instruction 2 immediately in the next clock cycle. So when instruction 1 is in the operand fetch stage, the next instruction would be in the instruction fetch stage. And of course, these two go here. Instruction 3 will come here. Now, the problem is, what if instruction 2 relies on a value that is written in instruction 1? For example, over here they're talking about clock cycles. So in the first clock cycle, instruction 1, second clock cycle, instruction 1 goes here, instruction 2 enters the if stage. But the problem is like this over here. How should I subtract, add? I should just copy paste this. Yeah. So let's get rid of 3. So let's say we have the first instruction is R2 plus R3 goes in R1. And the next instruction uses R1 and subtracts the value in R4 from the value in R1. Now the thing is, if we are doing this, if we are the problem is R1, R2, R3. Yeah, by the time instruction 2 is in the execute stage, like over here, by the time instruction 2 is in the execute stage, the value of R1 hasn't been written to yet, because that happens in the register stage. So this type of error is called read after write. Where did it go? I did this last stream. Where did it go? A hazard is defined as the possibility of erroneous execution of an instruction in a pipeline. This specific type of data hazard is known as read after write hazard. Here the subtract instruction is trying to read R1, which needs to be written to by the add instruction. In this case, a read succeeds a write. R1 is being read, and in the previous instruction, it is R1 is being written to, but the ordering is messed up because of the pipeline. I mean, if we waited for 1 to be complete, if we didn't bother optimizing, we waited 1 to complete the entire thing, and then 1 is done, and then we do instruction 2, that wouldn't be a problem. But they're trying to optimize, so they're trying to fit it in. Like they would bring the next instruction immediately after the first instruction is done. The next hazard is the control hazard. Here we have branch if equal foo, and then instruction 2, instruction 3. But the thing is, like, one enters, 2 enters, and in the over here 3 enters. But the thing is, it's possible that we might branch to foo, so this 2 and 3 would not be needed. We don't need to execute 2 and 3 because we may be branching to foo, but we don't know if we are going to branch to foo until we reach the execute stage. This is called the control hazard. The next instruction was supposed to be this. For example, the quality flag is on, so the next instruction in the pipeline is supposed to be this. So this causes an issue, but we don't calculate this until the execute stage. The outcome of the branch is decided in cycle 3. Cycle 3, 1, 2, and 3. Instruction 1 is here, instruction 2 is here, and instruction 3 is here. Let's communicate it to the fetch unit. The fetch unit starts fetching the correct instructions from cycle 4. Now, if the branch is taken, then instruction 2 and 3 should not be executed. Sadly, there is no way of knowing in cycles 2 and 3 about the outcome of the branch. So there is no way of knowing in the third clock cycle, we figure out whether it's equal or not. But in cycles 1 and 2, we don't figure this out. So we don't know whether to put 2 and 3 in the pipeline or not. So anyways, this is what we did last stream. Now they're going to talk about solutions. So read after write hazards. Now let us find a way of avoiding a read after write hazard. Let us look at our example again. Instruction 2 requires the value of R1 in the OF stage. However, at that point of time, instruction 1 is in the execute stage and it would not have been written back. It would not have written back the value of R1 to the register file. This instruction 2 cannot be allowed to proceed in the pipeline. Let us propose a nice sort-based solution to this problem. A smart compiler can analyze the code sequence and realize that the RAW hazard exists. Can introduce a NOP instructions between these instructions to remove any read after write hazard. So it's going to introduce no operation intentionally. So in order to avoid what we were talking about. So when sub instruction reaches the OF stage, this reaches the OF stage, the add instruction would have written its value and left the pipeline. The sub instruction will get the correct value. Note that adding NOP instructions is a costly solution because we are essentially wasting computational power. In this example, we have basically wasted 3 cycles by adding a no operation instructions. However, if we consider a longer sequence of code, then the compiler can possibly reorder the instructions such that we can minimize the number of NOP instructions. The basic aim of any compiler intervention is to ensure that there are at least 3 instructions between a producer and a consumer. Okay. So R1, R2, R3. R1 is being read over here. So I guess we can push this down, right? Wait. So we have this, and this. So R1, we can take this up there, right? And we can take this up here. And what about R10 to, okay, wait. So R4, so R1 is an issue, R8 and R10. So we need a NOP instruction. So in the if stage, one, two, three, 4, 5. Hold on. Let me think of one thing. I do have a question. Let's call this 1, 2, 3, 4. If 1 is here, it's writing to the register. And 4 is over here. Do the later stages happen first? If this and this are okay, 4 is in the instruction fetch stage and 1 is in the register stage. Would 4 read the new register value? I think it would, right? Yeah, I think it would. So I think 1 NOP instruction would be fine. Yeah. The first is the power of NOP instruction, and the second is the power of the compiler. Compiler is a vital tool in ensuring the correctness of the program and also improving its performance. Now for the control hazards. Let us now try to use the same set of techniques to solve the issue of control hazards. If we take a look at the pipeline diagram again, then we can conclude that there need to be a minimum of 2 instructions between the branch instruction and the instruction at the branch target. This is because we got the branch outcome and the branch target at the end of the execute stage. So the branch instruction is evaluated at the execution stage. That's when we can decide whether we want to put the instructions over here or not. They might potentially be on the wrong path after the branch target. The outcome have been determined at the execute stage, and we can proceed to fetch the correct instruction in the instruction fetch stage. Now let us consider these 2 instructions that were fetched when we were not sure of the branch outcome. If the PC of the branch is equal to P1, then their addresses are P1 plus 4 and P1 plus 8 respectively. They are not on the wrong path if the branch is not taken. However, if the branch is taken, then these instructions need to be discarded from the pipeline since they are on the wrong path. For doing this, let us look at a simple solution in software. Let us consider a scheme where the hardware assumes that the 2 instructions immediately after a branch instructions are not on the wrong path. Positions of these 2 instructions are known as the delay slots. Trivially, we can ensure that the instructions in the delay slots do not introduce errors by inserting 2 NOP instructions after a branch. However, we will not gain any extra performance by doing this. We can instead find 2 instructions that execute before the branch instruction and move them to the 2 delay slots immediately after the branch. Note that we cannot arbitrarily move instructions to the delay slots. We cannot violate any data dependence constraints, and we need to avoid read after write hazards. Secondly, we cannot move any compare instructions into the delay slots. If appropriate instructions are not available, then we can always fall back to the trivial solution and insert NOP instructions. It is also possible that we may find just one instruction that we can reorder. Then we need to insert one NOP instruction after the branch instruction. The method of delay branches is a very potent method in reducing the number of NOP instructions that need to be added to avoid control hazards. The reader should convince herself that to support this simple software scheme, we do not need to make any changes in hardware. Pipeline data path shown in figure 10.9 already supports this scheme. In our simple pipeline data path, the 2 instructions fetched after the branch have their PCs equal to P1 plus 4 and P1 plus 8 respectively. P1 is the PC of the branch instruction. Since the compiler ensures that the instructions are always on the correct path irrespective of the outcome of the branch, we do not commit any error by fetching them. After the outcome of the branch has been determined, the next instruction that is fetched either has a PC equal to P1 plus 12 if the branch is not taken, or the PC is equal to the branch target if the branch is taken. Thus, in both the cases, the correct instruction is fetched after the outcome of the branch is determined, and we cannot conclude that our software solution executes programs correctly on the pipeline version of our processor. To summarize, the crux of our software technique is the notion of delay slot. We need 2 delay slots after a branch because we are not sure about the 2 subsequent instructions. They might be on the wrong path. However, using a smart compiler, we can manage to move instructions that get executed irrespective of the outcome of the branch to the delay slot. We can thus avoid placing NOP instructions in the delay slot and consequently increase performance. Such a branch instruction is known as a delayed branch. A branch instruction is known as a delayed branch if a processor assumes that all the succeeding instructions that are fetched before its outcome is determined are guaranteed to be on the correct path. If the processor fetches n instructions between the time that a branch instruction has been fetched and its outcome has been determined, then we say that we have n delay slots. The compiler needs to ensure that the instructions on the correct path occupy the delay slots and no additional control or data write hazards are introduced. Compiler can also trivially introduce loop instructions in the delay slot. Okay, so we have this instruction, branch to full. Wait, what? Reorder the following piece of assembly code to run correctly on pipeline. Assume 2 delay slots per branch instruction. Branch to full. Okay, this will happen in the execute stage. So we'll put these two below branch to full. So by the time, branch to full will enter the pipeline, and then these two will also, by the time this is in the execute stage, these two will also enter the pipeline. So these two will be executed as they should. And then this won't be executed as it should. Up till now, we have only looked at software solutions for eliminating read after write and control hazards. However, compiler approaches are not very generic. Programmers can always write assembly code manually and try to run it on the processor. In this case, the likelihood of an error is high because programmers might not have reordered their code properly to remove hazards. Secondly, there is an issue of portability. A piece of assembly code written for one pipeline might not run on another pipeline that follows the same ISA. This is because it might have a different number of delay slots or different number of stages. One of our main aims of introducing assembly programs gets defeated if our assembly programs are not portable across different machines that use the same ISA. Hence, let us try to design solutions at the hardware level. The hardware should ensure that irrespective of the assembly program, correctness is compromised. The output should always match that produced by a single cycle processor. To design such a processor, we need to ensure that an instruction never receives wrong data. The wrong path instructions are not executed. This can be done by ensuring that the following conditions hold. Condition data log. We cannot allow an instruction to leave the OF stage unless it has received the correct data from the register file. This means we need to effectively stall the IF and OF stages and let the rest of the stages execute till the instruction in the OF stage can safely read its operands. During this time, the instruction that passes from the OF to the EX stage needs to be an OP instruction. Condition branch lock. We never execute instructions on the wrong path. We either stall the processor till the outcome is known or use techniques to ensure that instructions on the wrong path are not able to commit their changes to memory or register. In a hardware implementation of a pipeline, it is sometimes necessary to stop a new instruction from entering a pipeline stage till a necessary condition ceases to hold. The notion of stopping a pipeline stage from accepting and processing new data is known as pipeline stall or a pipeline interlock. The primary purpose is to ensure the correctness of program execution. If we ensure that both the data lock and branch lock conditions hold, then our pipeline will execute instructions correctly. You know that conditions dictate that possibly some stages of the pipeline needs to be stalled for some time. These stalls are known as pipeline interlocks. In other words, by keeping our pipeline idle for some time, we can avoid executing instructions that might potentially lead to an erroneous execution. Let us now quickly compare the pure software and hardware schemes in table 10.1 and see what the pros and cons are of implementing the entire logic of the pipeline in the hardware. Note that in the software solution, we try to reorder code and subsequently insert the minimum number of NOP instructions to nullify the effect of hazards. In comparison, in the hardware solution, we dynamically stall parts of the pipeline to avoid executing instructions on the wrong path and with wrong values of operands. Stalling the pipeline is tantamount to keeping some stages idle and inserting NOP instructions in other stages, as we shall see later. Comparison between software and hardware approaches for ensuring correctness. Portability limited to a specific processor. Programs can be run on any processor irrespective of the nature of the pipeline. We observe that the efficacy of the software solution is highly dependent on the nature of the program. It is possible to reorder the instructions in some programs to completely hide the deleterious effects of read after write hazards and branches. However, in some programs, we might not find enough instructions that can be reordered. We would thus be compelled to insert a few NOP instructions. In comparison, a pure hardware scheme which obeys the data lock and branch lock conditions stalls the pipeline whenever it detects an instruction that might execute erroneously. It is a generic approach which is lower than a pure software solution. Now it is possible to combine the hardware and software solutions to reorder code to make it pipeline friendly as much as possible and then run it on a pipeline with interlocks. Note that in this approach, no guarantees of correctness are made by the compiler. It simply spaces producer and consumer instructions as far apart as possible and takes advantage of delayed branches if they are supported. This reduces the number of times we need to stall the pipeline and bring together the best of both worlds. Let us now draw a pipeline diagram of a pipeline with interlocks. Let us consider the following code snippet. Here instruction 1 writes to R1 and 2 reads from R1. Clearly there is a read after write depend. To ensure the data lock condition, we need to ensure that that instruction 2 leaves the operand fetch stage only when it has read the value of R1 written by instruction 1. This is possible only in cycle 6. However, instruction 2 reaches the OF stage in cycle 3. If there had been no hazard, then it would have ideally proceeded to the execute stage in cycle 4. Since we have an interlock, instruction 2 needs to stay in the operand fetch stage in cycle 4, 5, and 6 also. So in cycle 5, 2 is here, 1 is here, 1 is writing to register. And then 2 is over here. 2 can now properly read the operands, right, from the register. And then it will move on to and then in cycle 7, it's going down to the execute stage. Let us refer to figure 10.14 again. At the end of cycle 3, we know that we need to introduce an interlock. Hence, the cycle 4 instruction 2 remains in the OF stage, and we insert a NOP instruction to the execute stage. This NOP instruction moves to the MA stage in cycle 5. And RW stage in cycle 6. This NOP instruction is called a pipeline bubble. A bubble is a NOP instruction that is dynamically inserted by the interlock hardware. It moves through the pipeline stages akin to the to normal instructions. Similarly, in cycles 5 and 6, also we need to insert a pipeline bubble. Finally, in cycle 7, instruction 2 is free to process to the execute stage. Subsequent stages. A bubble by definition does not do anything, and thus none of the control signals are turned on when the stage encounters a bubble. The other subtle point to note here is that we cannot read and write to the same register in the same cycle. We need to give preference to the write because it is an earlier instruction, and the read needs to stall for one cycle. There are two ways to implement a bubble. First is that we have a separate bubble bit in the instruction packet. Whenever the bit is 1, the instruction will be constructed to a bubble. Second is that we can change the opcode of the instruction to that of a NOP and replace all of its control signals by zeros. The latter approach is more invasive but can eliminate redundant work in the circuit completely. In the former approach, the control signals will be on and the units will be activated by them, and the units that are activated by them will be operational. The hardware needs to ensure that a bubble is not able to make changes to register or memory. What was there are two ways to implement a bubble. First, we can have a separate bubble bit in the instruction packet. Whenever the bit is 1, the instruction will be constructed to be a bubble. Second is that we can change the opcode of the instruction to that of a NOP and replace all of its control signals by 0. The latter approach is more invasive but can eliminate redundant work in the circuit completely. Wait, in the second approach, they're changing the opcode of the instruction. So, like, let's say instruction 2 was supposed to be here, but then they changed the opcode of the instruction, now it became a NOP instruction. So, is that what they're saying? We can thus conclude that it is possible to avoid data hazards by dynamically inserting bubbles in the pipeline. Let us quickly take a look at the issue of slow instructions such as the div and mod instructions. It is highly likely that in most pipelines, these instructions will take n cycles to execute in the execute stage. Each of the n cycles, the ALU completes a part of the processing of the div or mod instructions. Each such cycle is known as the T state. Typically, one stage has one T state. However, the execute stage for a slow instruction has many T stages. So, for slow instructions like div and mod, it will take many cycles to execute them. Each such cycle is known as a T state. Uh, why did we introduce a different word for it? Our execute stage for a slow instruction has many T states. Hence, to correctly implement slow instructions, we need to stall the IF and OF stages for n-1 cycles till the operation complete. For the sake of simplicity, we shall not discuss this issue further. We have the simplistic assumption that our pipeline stages are balanced and take one cycle to complete their operation. So now for control hazards, let us start out by considering the following code snippet. So branch f equal go to foo is over here. But the thing is, we don't know if it's equal or not. So these two will enter this pipeline regardless. We can insert the bubbles in the pipeline if the branch is taken. Otherwise, we do not need to do anything. Let us assume that the branch is taken. Then the pipeline diagram for this case is shown in figure 10.15. So one and then two enters, and in the clock cycle 3, 1, 2 is over here, 3 enters. But when this has successfully executed, and this is done, in the next clock cycle, 1 goes here. But let's say branch is in fact equal, and we are in fact branching to full, then 2 or 3 will get deleted, right? They will turn into NOP and 4 will enter. Is that what they're doing? The outcome of the branch condition of instruction 1 is decided in cycle 3. At this point, instructions 2 and 3 are already in the pipeline. Since the branch condition evaluates to taken, we need to cancel instructions 2 and 3, otherwise they will be executed erroneously. It thus convert to bubbles as shown in figure 10.15. Instructions 2 and 3 are converted to bubbles in cycle 4. Secondly, we fetch the correct branch target foo in cycle 4. We can thus ensure both the conditions, data lock and branch lock, by dynamically introducing bubbles in the pipeline. Let us now look at these approaches in some more detail. To ensure the data lock condition, we need to ensure that there is no conflict between instruction in the OF stage and any instructions in the subsequent stages. Conflict is defined as a situation that can cause a read after write hazard. In other words, a conflict exists if an instruction in a subsequent stage writes to a register that is read by the instruction in the operand fetch stage. There are two pieces of hardware that we require to implement the data lock condition. First is to check if a conflict exists. Second is to ensure that the pipeline gets stalled. Let us first look at the conflict detection hardware. The conflict detection hardware needs to compare the contents of the instruction in the OF stage with the contents of each of the instructions in the other three stages, namely execute, memory access, and read write. If there's a conflict with any of these instructions, we can declare a conflict. Let us focus on the logic of detecting a conflict. We leave the design of the exact circuit as an exercise for the reader. Let us outline the brief pseudocode of a conflict detection circuit. Let the instruction of the operand fetch stage be A, and an instruction in the subsequent stage be B. The algorithm to detect a conflict is shown as algorithm 5. A dot opcode is this, then does not read from any register, so return false. If a B dot opcode is this, does not write to any register, return false. Set the sources R source 1, R source 2. Okay. So the opcode is SD. Then oh sorry, if the opcode if A is a store instruction, then the source is the destination register. If opcode is the if A is a return instruction, then the source 1 is a return address. Set the destination. B dot read destination register destination goes here. If B is a call instruction, then RA the return address goes to here. Hold on. Check if the first operand exists. So has source 1 is true. If the opcode is not or moved, then has source 1 is false. Check the second operand to see if it is a register. Has source 2 is true. If it's not a store instruction and the I bit is 1, then source 2 is false. So if it's using an immediate instead of a register, then the second source is a number, right? It's not a register. Also, in this pseudocode, is it not possible to use an AND operator? Oh no, we can. They should have used AND over here. If source 1 is true, has source 1 is true, source 1 is the destination, then yeah, there's a conflict. If has source is equal to 2 and source 2 is the destination, then yeah, we have a conflict. Otherwise, we don't. Implementing algorithm 5 in hardware is straightforward. The reader can draw a simple circuit and implement this algorithm. All we need to do is a set of logic gates and multiplexers. Most hardware designers typically write the description of a circuit similar to algorithm 5 in a hardware description language such as Verilog or VHDL and rely on smart compilers to convert the description to an actual circuit. However, we shall refrain from showing detailed implementation of the circuit henceforth and show the pseudocode. We need 3 conflict detectors: OF2AX, OF2MA, and OF2 read write, register write. If there are no conflicts, then the instruction is free to proceed to the execute stage. However, if there is at least one conflict, we need to stall instruction and operand fetch stages. Once an instruction passes the operand fetch stage, it is guaranteed to have all of its source operands. Fetch unit instruction. This is the instruction fetch stage. Operation fetch stage. But then register write unit, it goes back here, right? Then this over here. Okay, data lock unit. Tall bubble. Let us now look at stalling the pipeline. We essentially need to ensure that till there is a conflict, no new instruction enters the instruction or OF stages. This can trivially be This can be trivially ensured by disabling the write functionality of the PC of uh, the PC and the instruction fetch and operand fetch pipeline register. Consequently, they cannot accept new data on a clock edge and thus will continue to hold their previous value. Second, we need to insert bubbles in the pipeline. For example, the instruction that passes from the OF to the execute stage needs to be an invalid instruction or alternatively a bubble. This can be ensured by passing an open instruction, hence the circuit for ensuring the data lock condition is straightforward. We need a conflict detector that is connected to the PC and the instruction fetch and operand fetch register. Till there is a conflict, these two registers are disabled and cannot accept new data. You force the instruction in the OF execute register to contain an op. The augmented circuit diagram of the pipeline is shown in figure 10.16. So what is the stall over here? So I'm guessing if this is like true, then it will introduce a bubble in the execute stage. Stall means like the fetch. It undoes what it did. Every time, like in every new clock cycle, it fetches the new instruction, right? So if stall is true, this will be paused, right? It is now assumed that we have a branch instruction in the pipeline. If we have delay slots, then our data path is the same as shown in figure 10.16. We do not need to do any changes because the entire complexity of the execution has been offloaded to software. However, exposing the pipeline to software has its pros and cons as discussed in table 10.1. If we add more stages in the pipeline, then existing executables might cease to work. Avoid this, let us design a pipeline that does not expose data slots to software. We have two design options here. The first is that we can assume that a branch is not taken till the outcome is decided. We can proceed to fetch the two instructions after a branch and process them. Once the outcome of the branch is decided in the execute stage, we can take an appropriate action based on the outcome. If the branch is not taken, then the instructions fetched after the branch instruction are on the correct path, and nothing more needs to be done. However, if the branch is taken, then it is necessary to cancel those two instructions and replace them with pipeline bubbles. Uh, the second option is to solve the pipeline till the outcome of the branch is decided, irrespective of the outcome. Clearly, the performance of this design is less than the first alternative, and that assumes the branches are not taken. For example, if a branch is not taken 30% of the time, then with the first design, we will do useful work 30% of the time. However, with the second option, we never do any useful work in the two cycles after the branch instruction is fetched. Hence, let us go with the first design in the interest of performance. We cancel the two instructions after the branch only if the branch is taken. We can call this approach predict not taken, because we are effectively predicting the branch to be not taken. Later on, if the prediction is found to if the later on if this prediction is found to be false, then can cancel the instructions on the wrong path. Basically, what they were talking about last time, where they turn instruction 2 and 3 into nope instructions, but they don't show the pipeline diagram. If the PC of the branch instruction is equal to P, then we choose to fetch the instructions at P plus 4 and P plus 8 over the next 2 cycles. The branch is not taken, then we resume execution. However, the branch is taken, then we cancel these 2 instructions and convert them into pipeline bubbles. We do not need to make any significant changes to the data path. We need a small branch hazard unit that takes an input from the execute stage. If the branch is taken, then in the next cycle, it converts the instruction in the instruction fetch and operand fetch and operand fetch and execute stages to a pipeline bubbles. The augmented data path of the with the branch interlock unit is shown in figure 10.17. Oh, they do show it over here. Data lock, and now we have a branch lock unit. Is branch taken? So bubble over here, a bubble over here. Pipeline with forwarding. Should I read this or should I leave this for next time? Okay, this chapter seems quite long, so I will leave it for next time then. Alright, so I will end it here. And yeah, I will see you guys next time. Bye.